This is the next in a series of videos about catalysts. In the last video, we talked about what a catalyst is and how it decreases the activation energy for a particular reaction and changes the mechanism. So in this video, we'll do an example of how to do a calculation involving a catalyst. So take a moment to write this problem down and pause the video here. So this is a kind of a wordy example. It says we have a second order reaction catalyzed by palladium 2+, which is a common catalyst in inorganic chemistry. With the catalyst at 450 Kelvin, the rate constant is this number and the activation energy is this number. And without the catalyst, the activation energy is this slightly larger number. Find the rate constant at that temperature for the uncatalyzed reaction. So this is very long. There's a lot of words here, but I can see that we're talking about two different situations, the uncatalyzed situation and the situation with the catalyst. Okay, so let's try and separate out some of that information because I'm already feeling lost trying to parse through that large paragraph. So we've got situation 1 and situation 2. Okay, situation 1, let's make that the catalyst, the catalyzed situation, because that's the one we know all the information about. And let's make situation 2 the uncatalyzed, because that's the one we're trying to solve for. We're trying to solve for the uncatalyzed rate constant. So we know some information here. We know for the catalyzed reaction, our activation energy is 23 kilojoules per mole. And we were given a rate constant of 4.8 10 to the negative fourth. And that was in inverse molar, inverse hours. And then for our situation 2, activation energy we know, that was 31. And the rate constant, that's the one we're trying to find. So the kind of information we have, we also have the temperature, was 450 Kelvin. So the only formula I know with activation energy in it is the Arrhenius equation. And there is a version of the Arrhenius equation that has 2 different points for 2 different situations. So I'd really like to use that one. The problem is that version of the Arrhenius equation only has 1 spot for activation energy. The 2 points are supposed to be temperature and rate constant combinations. But in this case, when we add a catalyst, we change the activation energy. So we're not going to be able to use that 2-point version of the formula. We're going to have to use one of the normal 1-point versions, which is fine. It just means we're going to have to do math twice. So we'll do the catalyzed one first, because we know the most information for that one. So the normal version of the Arrhenius equation is rate constant K equals the frequency factor A times E to the negative activation energy over the gas constant times temperature. So we know the rate constant, we know the activation energy, we know the temperature, and the rate constant is a constant. So the only unknown here is A. And so we need to solve for that unknown and use it for situation 2, because the frequency factor is going to be the same, even if the activation energy changes. So from here, we'll just plug in the numbers. 4.8 10 to the negative fourth equals A times E to the negative. And then instead of 23, remember that R is going to be in joules per mole Kelvin. So we should put this number in joules as well. 23,000 joules per mole. Gas constant 8.314 joules per mole Kelvin. And the temperature was 450. Everything should cancel out here. And then, we skipped our units for this one. It was inverse molar, inverse hour. All right, so we can just do a little bit of math. Simplify that a little bit. We should get e to the negative 6.15 approximately. And then we can solve for a, and we should get 0.224. And since e doesn't have any units, the units of the left side is going to be the same as the units for a. So this will also be inverse molar, inverse hour. It always has the same units as the rate constant. All right, so we have a, we have the frequency factor. That's not what we are trying to find, but it is something that we can use in situation 2 to solve for an unknown. Got to keep our eyes on the prize here. So we're going to use Arrhenius equation again. K equals A times E to the negative EA over RT. And for situation 2, we are trying to find the rate constant. We do now know the A, the frequency factor, because we found it for situation 1. We have the activation energy, the temperature, and the rate constant. So the reason we couldn't just start with the Arrhenius equation for situation 1 is because it has this unknown frequency factor in it. We need to take situation 1 where we know all the information to find that frequency factor before we can calculate values for situation 2. So we'll plug this stuff in, frequency factor, 0.224, inverse molar, inverse hour, times E, negative activation energy. Again, we'll put that in joules. This one is without catalyst, 31,000 joules per mole. This part looks the same, 8.314 joules per mole Kelvin, and 450 Kelvin. Kelvins cancel, joules cancels, moles cancels. And the rate constant will have the same unit as the frequency factor. Calculator says 5.6 10 to the negative 5th, inverse molar, inverse hour. And remember, it's always a good idea to go back and review to make sure that our number looks reasonable. So we saw that the activation energy was smaller for the catalyzed reaction. So that makes sense, because we know that the catalyzed reaction should happen faster. Smaller EA. And faster reaction should have a smaller activation energy and a larger rate constant. So for catalyzed, it was 10 to the negative 4th. And for uncatalyzed, it was 10 to the negative 5th. So catalyzed had a larger K. So that means our answer is reasonable looking, and we feel okay about our answer. In the next video, we will talk about how kinetics relates back to equilibrium and how we were secretly working with rate constants the whole time.